This is testing your understanding of forces and static forces in equilibrium. So we've got a situation where we've got a 0.2 kilogram mass, and there's a force upwards, we can call force upwards, and there's a force downwards. And I'm going to split the overall force downwards into the force downwards due to its own weight, and then the force downwards that's added, which is the 0.1 kilogram mass's weight. And that weight is mg, which is 0.1 kilograms times 9.8. So that is equal to 0.98 newtons. So 0.98 newtons. So if we add them all together, I'll give myself a bit of room over here. So if I add the upwards force to the downwards force to this mg, then I get zero resultant force. If I then rearrange that, I can find that if I just have the upwards force and the downwards force, then I get the negative of mg. And at this point, that's my resultant force, is zero. If I then take this away, so literally what I've done there mathematically, I've subtracted mg from both sides. If I take this away from both sides, then I end up with, rather than my resultant force being zero, my resultant force is negative mg. So it's a force in the opposite direction to the weight, which is upwards, equal in magnitude to the weight. So this shouldn't really be, I'd hope intuitively you can see this, it shouldn't be surprising that you can see if it's in equilibrium, if you've got lots of forces in equilibrium, so I've got lots and lots of forces in equilibrium, and then if I take one away from one side, then the resultant force is opposite in direction to the force I've taken away and equal in magnitude. So the resultant force on this system is mg, the mass of the 0.1 kilogram mass, multiplied by g upwards. So we get that the resultant force, the force is mg, so it's 0.98 newtons upwards, and then it causes an acceleration. The resultant force now causes an acceleration. So the acceleration is F over m. So that force is 0.98 divided by the mass, 0.2, and we end up with 4.9 meters per second squared.